So the new unit will be starting next class period. The unit 6 is going to be another scientific calculator only unit. We'll be doing some graphing in it, and we'll need to be able to figure out the things with the graphing algebraically. That's why you won't be able to use your graphing calculator. Our first topic is to look at how derivatives affect the shape of the graph. We're going to focus today on the second derivative. So we have two different functions here. We've got f and we've got g. F on the left, g on the right. They are both increasing functions. We want to think about what would their derivatives look like? What would their second derivatives look like? So let's kind of compare them. To start out, let's think about the original function f. Well, we know that f is increasing. Over here, g, our original function, is also increasing. So they have a similarity there. Let's think about what f prime would look like. F prime is your slopes. Our slopes here, because it's increasing, are always positive. So that means f prime is going to be positive since f is increasing. Now g prime, remember for g prime, look at your slopes of the original. The slopes are all going to be positive, so g prime will be positive. G prime is positive since g is increasing. And if we look at f double prime and think about what that might look like, well, f double prime is the derivative of f prime. F prime, we are looking at slopes. So f double prime, we want to think about how are the slopes changing. Well, think of this here as having like a slope of 0, and here roughly is a slope of 1, and then maybe like a slope of 2, and then like a slope of 3. So our slopes, they are changing, and as they are changing, they are increasing. Because the slopes are increasing, that means the second derivative must be positive. So it's positive since f prime, which we'll say aka the slopes, is increasing. Now when we look at g double prime and do the same thing, well, maybe that's like a slope of 3. That's roughly a slope of 2. That's a slope of 1, and here we're getting close to a slope of 0. So our slopes, while they are all positive, they are now decreasing. So the slopes are changing and getting smaller. So that means the derivative of our slopes, or g prime, the derivative of that g double prime should be negative. And that is since g prime, aka the slopes, are decreasing. Now, the two new pieces of vocab that we'll see, all the things on the left occur when the graph, and I'll say f, because that's our original graph, is concave up. And all the things on the right, so in other words, a negative second derivative, that occurs when g is concave down. Now, a simple example of a concave up function would be like an x squared. Okay, it is always concave up, it's opening up. A concave down would be like negative x squared. One that has elements of both would be like an x cubed. That point there, the first part is concave down, it's opening down. But then it switches, and now this part is opening up. So visually, we look for it as concave up and concave down. What's really happening is when it's concave down, the slopes are getting less, and when it's concave up, the slopes are getting more. And we can do a similar type thing with two functions that are decreasing. So here, f is decreasing. G is also decreasing. F prime is going to be negative since f is decreasing. Same thing, G prime is going to be negative since G is decreasing. Now when we look at f double prime, we want to think about how are the slopes changing. Well, here maybe we have like a slope of 0, then like a 1, or sorry, negative 1, then negative 2, negative 3. So here, f double prime is going to be negative since f prime, aka the slopes, are decreasing. So the slopes are getting smaller and smaller. So the change of f prime, or its derivative, f double prime, must be negative then. And g double prime, think of this as like a negative 3. This is like a negative 2, negative 1, and then a 0. So as you go from negative 3, negative 2, negative 1, 0, you're actually getting larger. So g double prime here is going to be positive since g prime, aka the slopes, are increasing. And you might be able to start picking out visually. So the one on the left is opening downward. So this would be concave down. And on the right, this one's opening upwards, so this is concave up. So you might be able to tell from this slide and the previous one, the key distinction of being concave down is that your second derivative will be negative in that part. And the key distinction of concave up is that your second derivative will be positive in that part. And that's how essentially we are going to test for concavity. Concavity is the general word meaning deciding if it's concave up or concave down. So again, just the thought process that you have to go through. If you want to be thinking about what f prime is going to look like, think about what are the slopes going to look like. So draw on some slopes, see if they're positives or negative. If they're positive slopes, then f prime will be positive. If they're negative slopes, then f prime will be negative, and same thing for g prime. To see what f double prime or likewise g double prime would be, see how are the slopes changing. If the slopes are increasing, then the second derivative will be positive. If the slopes are decreasing, the second derivative will be negative. If the second derivative is positive, that will yield a concave up scenario like the one on the left. And if the second derivative is negative, it will yield a concave down situation like the one on the right. So here's your formal definition. If the graph of f lies above all of its tangents, it is called concave upward. So if we look back here at these tangent lines, notice on the left, every one of those tangent lines, the graph is above the tangent lines. And on the right, notice in the concave down, the graph is below the tangent lines, and that's what we'll see for its definition. So the second one there, if the graph f lies below all of its tangents, it is called concave downward. The two biggest things is knowing that a negative second derivative goes with concave down, a positive second derivative goes with concave up, and to identify how they are going to look, because you will need to sketch graphs that contain those qualities. Okay, so just one last time looking at this, notice when your derivative f prime is increasing, so that's the same as saying when the slopes are increasing, therefore the derivative of f prime, f double prime, is positive, and that creates a concave up. And likewise, if that second derivative is negative, meaning the slopes were decreasing, it'll yield a concave down. Now let's look at a funky graph. This is to hopefully help you start to pick out visually if it's concave down or concave up. Well, from our beginning A to B, that section is concave down. But at B, it then switches to concave up all the way till C, and then C to D, it's concave down again. D to E, it's concave up, and then from the x values from E to P, it's still concave up. From P to Q, then it's again concave down. Now what the pluses and minuses represent is to remind you that when it's concave down, the second derivative will be negative for all those x values. And when it is concave up, the second derivative will be positive for all of those x values. Our next piece of vocab is what's called an inflection point. An inflection point is a point on the original graph, f of x, where the curve changes from either concave upward to concave downward or vice versa. If it happens to be concave upward and stay concave upward, then that is not an inflection point. Same thing if it's concave downward and stays concave downward. That is also not an inflection point. And so we can identify the inflection points from that graph we just saw. Here's the same picture. B, C, D, and P would be considered inflection points. At B, it changes from concave down to concave up. That's what makes it an inflection point. C is because it goes from concave up to concave down, and D goes concave down to concave up. At P, it's going from concave up to concave down. Now notice the one that has the X there. On the left of it is concave up. On the right of it is concave up. When you go from concave up to concave up again, that's no inflection point. Okay, notice that it forms a kink there, which we've seen those in graphs before. So your concavity test, if the second derivative is greater than 0, so in other words positive on an interval, then it must be concave upward on that interval. If the second derivative is negative on some interval, then it's concave down on that interval. And this is going to be the very useful one for determining concavity. I'll show you a second way you can determine if it's concave up or concave down in a second, which is not, it's a little bit more work, so most cases you'll probably use this. So the other one that I was talking about is what's called the second derivative test. If you have a point where the first derivative is 0, you can then test that x value in your second derivative. When you test that x value in the second derivative, if it's positive, it will be concave up, meaning you must have a local minimum. And we've talked about that if it's positive in the second derivative, it must be concave up. We just noted that if the first derivative is equal to 0, then it could potentially be a local max or local min. So this is saying if it's equal to 0, and then you test that x value in the second derivative, if it becomes positive, since it's then concave up there, that must have been a minimum. And the reverse, if you get a first derivative value to give you 0, and then plug that x value into the second derivative and you get one that's negative, that means you must be concave down, causing a local max at that point. Now, because this causes you to have to go to the second derivative, you're usually, unless it's specifically asked to do the second derivative test, you're usually going to do what we've done before to find local mins and maxes, which is use the first derivative and just see where it changes from plus to minus or minus to plus when you do your plugins on your number line. So here, notice at that point P, your first derivative is a horizontal tangent line, so it's 0. When you plug it into the second one, you would end up getting a positive number, which means it's concave up, meaning you must have a local min. The second derivative test is inconclusive if you get back 0 when they're for the second derivative. What that means is it could be a max, it could be a min, or it could be neither. The fact that this could sometimes be inconclusive is another reason why using the first derivative test to determine local maxes and mins is often a better idea. Another problem with this one is if f prime of c doesn't exist, f double prime of c doesn't exist, then we can't use the second derivative test. We would have to use the first derivative test anyway. So we're going to use our knowledge now of first derivative and second derivative to try and sketch a function that has these qualities. What we're going to do also before we sketch the graph is list out what each of these things really means. It says we want the first derivative to be greater than 0 on the interval negative infinity to 1. Well, if the first derivative is greater than 0, it means the first derivative is positive. If the first derivative is positive, it means the function is increasing. So this means we know it has to be increasing from negative infinity to 1. And over on the right, that next section needs to be less than 0, so that means it's going to be decreasing from 1 to infinity. To our second criteria, it says the second derivative needs to be positive on those two intervals. Well, we've just talked about that when the second derivative is positive, that means concave up. Now, you'll see me use the abbreviation a lot, and you're welcome to use it too. For concave up, just writing CU, and for concave down, writing CD. Kind of like we do INC for increase and DEC for decrease. This is kind of the shorthand. So this means we're going to be concave up from negative infinity to negative 2, and also 2 to infinity. And that means we'll be concave down, because the second derivative is negative, from negative 2 to 2. And the last part, we've got some limits. As we go to negative infinity for x, that means when we go really far to the left for x, we need to approach a y value of negative 2. So that means we want to approach negative 2 as we go to the left. And again, when I'm saying negative 2, that means approach the y value of negative 2. And the limit is x goes to infinity, so as we go to the right, we want to approach 0. And again, when we say approach 0, we're talking y values. So if we're switching from increasing to decreasing at 1, increase to decrease switch is a max. So we can help get this plot going by drawing a max at an x value of 1. So we'll pick a value somewhere up here. Now, we also switch from concave up to concave down at both negative 2 and positive 2. So that means we must have inflection points at those spots. So we'll put little points in somewhere at negative 2 and somewhere at positive 2. And we want to approach -2 as we go to the left, and we want to approach 0 as we go to the right. If you just draw in now your concave ups and concave downs, the increasing and decreasing should take care of itself. We're going to be concave up from -∞ to -2, and we'll also make sure we flatten out at that asymptote. So we'll look. We'll look something kind of like this. Notice that whole section we're concave up. And then from here to the green point, our maximum, will switch to concave down. So it'll look something like that. And then from, oops, sorry, I got to keep going to the blue point, sorry. So that's all concave up. And then it'll switch to concave down. And it'll flatten out at 0. Now, in reality, it probably won't be quite as drastic when we draw it, but it's hard to draw it and make it clear that you have inflection points at those points. So plot the maxes and mins, plot the inflection points, and just draw in where you're concave up and concave down. And now if we check, we need to increase all the way from -∞ to 1, which is occurring, and we need to decrease from +1 all the way to +∞, which is also occurring. All right, we're going to start with a function now, do our derivatives, and use the information that we gather to then sketch the curve ourselves. So let's start out, let's take the first derivative. That'll be 4x cubed minus 12x squared. We'll want to set that derivative equal to 0, and in doing so, I'm going to pull out a 4x squared, leaving x minus 3. And when we set those equal to 0, we'll get x equals 0 and x equals 3 as our critical values. Put 0 and 3 on the number line. Remember, when we test our gaps, we're testing in the derivative. It's easiest to plug into the factored form when we pick something like -10 million. -10 million squared will be a positive. -10 million minus 3 is a negative. A positive times a negative is a negative. If we pick something like 1, the left-hand part will be positive. 1 minus 3 will be negative. A positive times a negative is a negative again. And if you pick something like 10 million, you'll have a positive times a positive to give you a positive. Note, at 0, it is neither a max or a min. It's decreasing on either side of it, so it's going to end up kind of looking like that, like a -x cubed would. And we will have a min at 3 because we're going from negative to positive. So we'll have a local min at 3 comma something. This is a point on the actual graph, so we want to plug into the original function. When we plug in 3 to the 4th will give us 81. 3 to the 3rd is 27. 27 times -4 will end up giving us -108, which in the end will give us -27. So 3 comma -27 will be a local min. We'll carry on now and do the second derivative. Now, when taking the second derivative, it's probably going to be easiest to work with this part here. So that'll give us 12x squared minus 24x. We'll set that equal to 0. And in doing so, I'll pull out a 12x, leaving us with x minus 2. Setting them equal to 0, we'll get values of x equals 0 and x equals 2 to put on a number line. Our process is going to be similar to what we do with the first derivative. So we'll have 0 and 2 on here. We'll take numbers from the gaps and plug it into our second derivative. Factored form is usually the easiest. So something like -1,000,000, you'll get a negative and a negative, so a positive. Something like 1, you'll get a positive and a negative, so a negative. And like something like a positive million will be positive times a positive, so a positive. Notice each of the sections where it's positive, you'll be concave up. Where it's negative, you'll be concave down, and where it switches, there'll be an inflection point. Just a reminder, an inflection point is just where it switches from either concave up to concave down or vice versa. So we're going to have a point at 0, comma something and 2, comma something. These are points in the original function, so we have to plug it back into the original function. When you put in 0 for x, you get 0 minus 0, which is 0. When you put in 2 for x, 2 to the 4th is 16. 2 to the 3rd is 8, times a negative 4 is negative 32, so you'll get back negative 16. So we have found our concavity. We found our points of inflection, and we found our local minimum and maximum. In this case, we just had a minimum. Now we have to sketch the graph. So plot your inflection points and your maxes and mins. So we've got 0, 0. We've got 2, negative 16. And we had 3, comma, negative 27 as our minimum. And just drawing your concave ups and concave downs. We need to be concave up from negative infinity to 0, so something like that. We need to be concave down from 0 to 2, so something like that. And we need to be concave up for the rest of the graph, making sure we have a minimum at that negative 3, negative 27. So we'll look something like that. Notice we are decreasing all the way from the left till we get to the 3, and then we're increasing after that, which confirms. So usually the increase, decrease is kind of like a check, and you use the concave up, concave down to actually draw the graph. Okay, here's a nice version of the graph, okay, with a little bit smoother curves and a better scale, which is very similar to what we saw. Now, one last graph to look at. We've got a graph here that shows a population of bees. It looks a lot like a logistic function, something that if you were in Regents pre-calc last year, you saw with the rumor mill when you looked at the spread of a rumor. How does the rate of the population increase change over time? Well, to start out, it starts to increase the amount it changes, but then that increase starts to slow down. When is this rate the highest? So when is the change the highest? That's like saying when is the slope the highest? Well, the biggest slope is roughly somewhere in here, so around at 12. And we are in weeks, so we've got about 12 weeks. Over what intervals is P concave up, and what intervals is it concave down? Well, 12, where it's the steepest, that's where it changes from concave up to concave down. The slopes are increasing until they get to 12 and then decreasing after there. So we're concave up from 0 to 12, and we are concave down from 12 to 18. That's all for today's video. We'll see you next class period.